Welcome to the lecture Reflection and Refraction. Upon successful completion of this unit, you should be able to describe reflection of light and the law of reflection, describe and calculate the refraction of light, describe the dispersion of light, apply the principle of least time to reflection and to refraction, and calculate the conditions for total internal reflection. We've already just started with describing light as an electromagnetic wave. However, Hertz and Einstein also discovered that light can behave as a massless particle or quanta packet of energy. The energy of the photon is proportional to the frequency of the electromagnetic wave, and the equation of this is the energy equals h times f. H is Planck's constant, 6.63 times 10 to minus 34 joules seconds. This is one of the most important fundamental constants of physics. It actually determines how far back in time we can look toward the Big Bang, and also determines the edge between where quantum mechanics rules and where classical mechanics rules. Light can actually behave as either a particle or wave, and it depends on the experiments you do. And light will travel in waves in vacuum and as particles when it interacts with matter. We're going to investigate a little bit of both of this. In this section, however, we will model light as a ray, a straight line. Light will generally travel in a straight line unless it encounters a gravity field, and of course that would be the subject of general relativity, or a medium with a different index of refraction, and of course that's this chapter. And we will approximate the travel of light as a straight line called a ray. This is the field of geometrical optics. When light encounters a boundary between two transparent media, typically a reflected ray appears and also a refracted ray. Now, we will ignore the fact that a lot of times there is some absorption. We're going to assume that the media are perfectly transparent. Okay, the law of reflection you've probably heard of or figured out for yourself. It basically says the angle of incidence equals the angle of reflection. Both of the rays will lie in the plane of the incidence. Yeah, the angles are always measured relative to the normal, not the surface. So the reflected light is, of course, the light that bounces off the surface at the angle of reflection relative to the normal. Be very careful with that. All it says is this angle equals that angle. Okay, now there's two basic kinds of reflection. Diffuse reflection occurs when light reflects from rough surfaces. The borderline for rough and smooth is if the rough surface, the size of the rough patches, are less than 1/10 of the wavelength of the light, then the surface will act as if it's smooth. So that's the way you can tell that. The law of reflection will actually still hold even for a rough surface, but the surface itself is so rough that the reflected rays don't come off at a single angle. Okay, they still obey the angle of incidence equals the angle of reflection, but the normals here, the normal here is there, the normal of this surface is here. You know, you can see in all these angles, all these light rays are reflected different things. So you don't need to be in a specific place to see the reflected light. It sort of comes off as diffuse light. Specular reflection comes from a mirror or a smooth surface at a specific angle determined by the angle of incidence. And at that point, your eye has to be just exactly at the right spot to catch the reflected light. And you can see this if you take a laser pointer and reflect it off a shiny surface like a mirror. Don't reflect it into your eyes. Okay, now we say the light's reflected when it's returned in the medium from which it came, and we call this process reflection. And how does this work? Well, remember I mentioned the electrons are what matters. When light illuminates a material, electrons in the atoms of material will move more energetically in response to light. In other words, they get excited by the light because the light has oscillating electric fields. And the electrons are charged particles, so they can interact with the electromagnetic radiation. And metals with loose delocalized electrons are good conductors. And I mentioned this when we talked about metals being good conductors. This is also what makes them shiny. This is why they're good reflectors when you polish them to a smooth surface. Of course, the energized electrons, they just re-emit the light by which you see the material. Now, there's something called the principle of least time. It's sort of like me when I commute into work. I always try to pick the path that takes the least amount of time. And light does the same thing. Light's an excellent commuter. So light takes the quickest path going from one place to another, and this is called Fermat's principle of least time, or Carol Whistle's principle of least commuting time. Now, pretend you're going to be a beam of light. Okay, and you have to go to point B from point A, and you're not allowed to go through here. You have to bounce off a surface, and your task is to find the shortest time to go from this path, okay, from A to B by reflecting off the mirror. So what you do is you, being a smart beam of light or a smart commuter, you construct an artificial virtual point, and this, of course, will be the same distance below this surface inside the material, and it's virtual, so it's imaginary, as this point is above the surface. If you can look at these triangles in here, you can see that the shortest distance between A and this artificial point is actually this straight line. And light wants to do that. but it can't go here, okay, because light reflects off the surface. So what happens is this straight line intersects the mirror at point C, right here. And that's the point of reflection, because this triangle and this triangle are going to be the same. So by geometry and inspection, we can see that the angle of incidence, of course, that will, of course, be relative to the normal, which isn't shown here. So this angle here has to equal that angle, because these two triangles are similar. Okay, so that says the angle of incidence equals the angle of reflection, or theta 1 prime equals theta 1. Now, again, remember, you're always measured relative to the normal. You should repeat this thing to yourself a couple times a day. Angles are normally measured relative to the normal. Because where people make mistakes in this stuff, you're given an angle relative to the surface and you forget to convert it. Okay, now the angle of refraction, and we're going to talk about how do we figure out the angle of reflection. We're going to be using something called Snell's law. And you have a reflected ray, and you can see here's a beam reflected and some of it's refracted. Some of it gets reflected and some gets refracted. So if you looked at this picture drawn like this, here's the incident ray, represented by a line with these crosshatches on it. Here's the reflected ray, and here's the refracted ray. And it turns out that if you look at this angle, and this angle, and this, there's a relationship between these angles and the indices of refraction of the two material, which is, of course, why they call them the indices of refraction. And it turns out that N2 sine theta 2, okay, so N2 sine theta 2 equals N1 sine theta 1. What are N1 and N2? They're dimensionless constants called the index of refraction. This is associated with the medium involved in the refraction and also the wavelength of the light, and is directly related to the speed of light in the medium. We'll talk more about that, what the exact relationship is. Now, N is always greater than or equal to 1. We'll say that again, too. The refracted light is the light that travels through the interfacing surface that separates the media. And be very careful. The words reflected and refracted are only different from each other by 2 letters. So when you read test questions, especially here, read carefully. Make sure you don't make the mistake, and I've seen people do this. Reverse these two. Absolutely read very carefully, because I don't know why, and I didn't invent this. It was up to me, I come up with completely different names, because that's really annoying. Why does light bend toward or away from the normal? And how can you tell which way it's going to do it? It all depends upon the indices of refraction. Okay, now light always takes the path of least time, like me when I'm commuting to work. I am very good at picking out what is the fastest commute. And light does the same thing. Light's job is to get from A to B, and it will refract to minimize the time it takes to get from A to B. Suppose you're a lifeguard and you're watching the ocean. Your lifeguard stand is here and somebody gets in distress over here. You realize maybe you can run on sand maybe at 16 miles an hour. It's a short sprint. But you can at most only swim 2 miles an hour. You're going to try to spend as much time on the sand as you can. And you're going to go over here before you start toward the person in distress, because you can run faster than you can swim. So this means this N here, the index of refraction here, is lower in the sand than it is in the water. So you minimize the time you spend in the slower medium by minimizing the path in the water. And you have automatically set up, especially if you're an experienced lifeguard or you have any kind of brains at all, you set it up so your path bends toward the normal when you encounter the water. Here's the normal, right here. And notice this angle here is smaller than that angle there. So what's going on here? Here's the lifeguard stand. Here's the swimmer. Here's the incident angle here in the sand. Here's the refracted angle in the water. Refraction in glass. Light going from A to C, okay, right here, big C here, is going to follow a less inclined path in the glass. Why? Well, light can travel very fast in air. It almost travels as fast in air as it does in vacuum. Glass, it slows down by quite a bit, depending on what type of glass you've got. It might be slow by 30, 40, 50%, depending on the type of glass. So it's going to want to spend as least amount of time. It's going to have the least path in the glass. So it's going to bend toward the normal as it encounters the glass itself. And then when it comes back out into the air, it's going to say, woo, I'm back on the freeway. I'm back in vacuum almost, and I can bend away from the normal. Now, this right here, there's no advantage to bending. So when you have something that is perpendicular to the surface, that is parallel to the normal, the angle of incidence is then 0, there's no refraction. Here you have refraction here and here. One toward the normal as it encounters the higher index of refraction, the slower medium, and one away from the normal as it encounters the faster index of refraction, lower index of refraction. Okay, now here is a picture here. And this is basically the same as here. Now, this is fully reversible. Even though the source is over here, it might be easier to start over here. It doesn't make any difference. It'll work either way. It's fully reversible. So whatever is the easiest way to do it, do it. So the index of refraction, given the symbol n of a material, indicates how much the speed of light differs from its speed in vacuum. It's a ratio of the speed of light in vacuum to the speed in the material. It's a property of the material and also dependent on the wavelength of light in most cases. In equation form, n is c over v. C is the speed of light in vacuum. That's 3 times 10 to the 8 meters per second. V is the speed of light in medium. N is always greater than or equal to 1 because V is always less than or equal to C. Medium with a high index means the light slows down. So large N is a slow medium, and light will bend toward the normal to minimize the time it spends in that medium. Now, N is greater than or equal to 1 because nothing travels faster than light in vacuum. This, you want to remember this. Okay, if you get a trick question, I'll give you a question where you calculate it and N is greater than 1. The answer to that, you can't have that. We're going to take 3 different examples. Okay, so it's coming from the medium of N1 and going toward the medium of N2. We're going to ignore the reflected rays because we've already done that. We only care about the refracted rays. Okay, the first and the easiest thing is N1 equals N2. So this means these two mediums are the same. They have the same index of refraction. And when that happens, light gets no advantage just bending toward or away from the normal. It's not going to make any difference. It doesn't bend at all. And theta 2 equals theta 1. Kind of a trivial case, but I always cover it anyway because you never know. At this place, if the index N2 is greater than N1, okay, so the next index is larger, that means N2 is greater than N1. The light will slow down in the second material, and then it will try to shorten its path, and it does that by bending toward the normal. In this case, theta 2 is less than theta 1. It's bent toward the normal. Remember, you're always measuring relative to the normal, not relative to the surface. Be very careful with that. Okay, the next one here, next index smaller means ray bends away from the normal. So you're coming from a higher index of refraction to a lower one. So N2 is less than N1, and the light can go faster here. So it can lengthen the path through the fast medium. So we'll bend away from the normal, and theta 2 is greater than theta 1. Now this next slide you might want to put in your notes somewhere, along with the drawings. Okay, copy them into your notes. You can bring anything you handwrite with you to a test. Hint, you definitely want to put this in your notes. Okay, so light is going from N1 to N2. If N2 and N1 are the same, V2 equals V1, theta 2 equals theta 1, the light is not bent. If N2 is greater than N1, V2 will be less than V1, theta 2 is less than theta 1, light bends toward the normal because you're going into the slower medium. If N2 is less than N1, V2 will be greater than V1, theta 2 will be greater than theta 1, the light will bend away from the normal because it's going into the faster medium. Now, with this, I always list the second medium first for these. Compare the two ends. It's always what you're going into that counts relative to what you're coming out of. Compare the two ends. Remember, the high end equals slow speed, more bending toward the normal. And never, ever forget that the angles are normally measured with respect to the normal, not the surface. Everybody makes mistakes with there. You make mistakes like that, write it down every time you do your homework. Write this down. Every single homework problem. Angles are normally measured relative to the normal. It'll save your butt. And then you get in the habit and you won't make the mistake on the test. Okay, now there's all kinds of illusions caused by refraction. Now, objects underwater appear closer to the surface. You've probably noticed this. Yeah, you look for something at the bottom of the pool and you try to bend and pick it up, and what happens? You miss it, right? Yeah, it looks like it's here instead of there. It makes it really hard to catch a fish with your hands or a net unless you look straight down from above. It's very hard to shoot fish from the side or spearfish them from the side unless you go directly above them. This is also an extreme danger in floods. Water appears about 30% shallower than it really is. So people make this mistake all the time. They'll drive their car into floodwaters because it doesn't look that deep. On top of that, when the water gets really deep, it can be moving really fast, but it looks like it's standing still. You all ever heard the expression, still waters run deep? It should be still looking waters run deep. And they run fast because they can. It only takes a few miles an hour. Ankle deep water, 6 miles an hour, will knock you off your feet. Water foot deep will take a car away. Water 2 feet deep will take just about any SUV you have away. And the road can also be washed out from underneath. So never drive through floodwaters. Turn around, don't drown. The Weather Channel's right. Okay, another illusion caused by refraction. Do you realize that the sun actually rises 2 minutes later than it seems to and sets 2 minutes earlier than it seems to? Yeah, kind of cool. Now, we don't usually consider the air's index of refraction. It's less than 1% different from a vacuum. So we usually ignore it. But the atmosphere, especially when you're looking at a grazing angle like this, is thick. So there's a lot of air to look through, and even a tiny difference is enough to cause a refraction. It's actually enough to bend the light half a degree. Coincidentally, that is the apparent size of the sun as seen from the Earth. So when the sun's lower edge, that's called its lower limb, by the way, is just touching the horizon, in reality, the sun is just under the horizon, completely below the horizon. Kind of cool. You never knew that, did you? A little tidbit from astronomy. Okay, now there's another way to look at refraction. Again, remember, it's caused by a change in the speed of light at the interface. And if you were pushed a loaded grocery cart across the parking lot and then either encountered snow, someplace where the snow had been plowed off the lot, or encountered grass, and you try to push it, you come approach it at an angle like this, something with its angle relative to the normal. And when you try to push it through, it has a tendency to bend the cart. The cart wants to go this way, bend toward the normal. Yeah. Okay. Why? Because the wheel hits this first, okay, and then that causes a torque here and bends it toward the normal. You keep pushing here, and this wheel is already resisting you more than that wheel is. So the whole thing bends toward the normal. Light acts exactly the same way. So it's another way to remember that. This is a higher index of refraction. It's a slower medium than this is, and the thing will bend toward the normal. Now, here are some indices of refraction, and you can copy this table into your notes and take it with you, use it in your homework and stuff like that. They're also available in the book, and you can look them up online, but on the test, it's a good idea to have this with you. I'll usually give you the index of refraction that is involved, but, it's a good idea to copy it down anyway. Notice diamond. Diamond has the highest index of refraction, and that's one of the reasons diamonds look so pretty and sparkly. Part of what gives them that scintillation that they get where they flash colors at you. Okay, notice air here. Air is 1.0002. It's almost exactly the same as vacuum. In most cases, you neglect that difference. Now, how do you tell when not to neglect it? Okay, well, if you look at the answers on a problem, you see a lot of sig figs in the answers, then don't neglect it. Okay, but normally you can say it's 1.00. Usually 3 sig figs are enough. Some tips here. N is always greater than or equal to 1. N is C over V. C is 3 times 10 to the 8th meters per second. That's the speed of light in vacuum. V is the speed of light in the medium, and V is always less than C, which is why N is greater than or equal to 1. The greater N is, the more the light will slow down and refract toward the normal when it hits the medium. We will also investigate the way that N actually does. Now notice they say this is a wavelength here at 589 nanometers. That's yellow light. Okay, so all of these are just for that light. Now, in reality, most of the time you don't have to worry too much about that, but it's actually kind of important and it's kind of cool too. Okay, now what happens to light when it encounters a different medium? It may slow down, speed up, or do nothing. It may or may not bend toward or away from the normal. What about the wave? We talked about what is speed, but how about the wavelength and frequency? Well, you can kind of imagine, because there's a relationship between speed, wavelength, and frequency, that there might be some sort of issue with some of this. Okay, so we have V equals F lambda. It turns out the frequency does not change. So all the frequencies are the same. But frequency is V1 over lambda 1, and that is equal V2 over lambda 2. And we know that V1 and V2 are not going to be the same, but there's a relationship. V1 will be C over N1, and V2 will be C over N2. We can eliminate the C's, and we can come out with this relationship to get the wavelengths in different medium. So lambda 2 will be lambda 1 times the quantity N1 over N2. If the medium is a vacuum, then N1 will be 1 by definition. If you're going from a vacuum then into something else, then lambda 2 equals lambda 1 divided by N2. And usually we can, if it's air, we just assume that it's 1. unless we had to be extremely precise. So what happens is the wavelength will decrease and the light will slow down as it enters the medium with a higher N. Nothing is faster than vacuum. So you're always going to have, if that medium 1 is a vacuum, the medium 2, the light's going to be running slower in it. Light in a vacuum is as fast as it can go. Chromatic dispersion. Chromatic dispersion is when light separates into colors. So in other words, white light has all the different colors in it. And when it encounters a medium with an index of refraction that is higher than the air, then, and you have the shape this way, this is a prism, then you have a splitting of the colors. It's because the index of refraction in most media varies with the wavelength of light. And typically, the shorter wavelengths are bent more than the longer wavelengths. Here's a graph of this. Here are the shorter wavelengths. Notice the indices of refraction are higher at this end of the chart than they are at that end of the chart for most of these. The index of most materials depends upon wavelength, and usually it's higher for the shorter wavelength. So blue will typically have a higher N than red does, and blue light gets bent more than red does. Now, this is good for prisms, rainbows, the diamond color sparkle. That's what gives it that scintillating color. Okay, that's because of this. But it's bad when you talk about chromatic aberration in lenses. Okay, now we have an example here. We're going to reflection. It's hard for you to say this. Reflection with an L and refraction with an R of a monochromatic beam. Mono means one color. So a beam of monochromatic light reflects and refracts at point A on the interface between material 1 has an index of refraction of 1.33 for N1, and with material 2, index of refraction of 1.77. Now this is a multi-part question. This is just the first part. We'll later do this. The incident beam makes an angle of 50 degrees with the interface. Be very careful with that. When they say with the interface, that's not relative to the normal. It's 40 degrees relative to the normal. What is the angle of reflection at point A? And you probably immediately answer 40 degrees. What is the angle of refraction there? You're going to have to use Snell's law. And this is the first of a two-part problem. And from now on in, WRT means with respect to. Now you should work on this problem at home and before the lecture or before the video. The physics of this is reflection, refraction, Snell's law, all angles. Put this in your homework. When you write this down, the physics, all angles must be with respect to the normal. If you don't do that, I guarantee you're going to make the mistake. And then why is it wrong? And I'll be getting emails from you saying, why can't I get this problem right? The first thing I'll look at, did you set it up correctly for measuring angles relative to normal? 9 times out of 10, that's what it is. So if you put this down, if you can't get the right answer, go back and look at that and see if you actually did it that way. Okay, then you want to write down everything else. Okay, write down N1 is 1.33, N2 is 1.77. The angle is with respect to the surface, so we're going to have to change it to respect to the normal. It'll be 40 degrees. Theta 1 prime, theta 2 prime, theta 2 was what we're looking for. The easiest one is angle of incidence equals angle reflection, and you probably just immediately knee-jerk reaction 40 degrees. But we also need this part, N2 sine theta 2 equals N1 sine theta 1. And of course, again, we're going to remind ourselves the angles are respect to the normal. Okay, the first thing is the angle reflection. And we figured this out, it's 40 degrees. The second one is Snell's law. We need to be very careful to use this correct angle here. And we're going to solve it for theta 2. Theta 2 will be the inverse sine of N1 over 2, N2 times sine theta 1. So theta 2 will be the inverse sine of N1, which is 1.33 divided by 1.77, that's N2, times the sine of 40 degrees, not 50. It comes out to be about 29 degrees. And that's the angle of refraction in medium 2 with respect to normal. So this is this angle right here, theta 2. And we should check this at this point. N2 is greater than N1. So theta 2 is going to be less than theta 1. And that's expected because it's slowing down in this medium here. It's going to bend toward the normal. Okay, this is the second part. We're looking at this interface now. The light that enters the material 2 at point A then reaches point B on the interface between these two, material 2 with an index of refraction of 1.77 as before, and material 3, which is air, which will have an index of refraction of approximately equal to 1. Okay, the interface through these two is parallel. So this is parallel to that, and when they draw like this, most times it is. Now at B, some of the light will reflect, okay, and maybe come out through this material, but we're not worrying about that. And some of it will refract into this other material, into the air. What is the angle of reflection? You probably could figure that out right off the bat, but be very careful with it. What is the angle of refraction? And of course, you should have done this at home before you view the videos. Okay, we have the same physics as before. Reflection, refraction, Snell's law. Again, remind ourselves, all angles are measured relative to the normal. But now we're going into an index with a lower index of refraction. We're going to expect the light here to bend away from the normal as it comes out into the air. Okay, so we write down everything we know. This is repeated from the first part of the problem, so it's nothing new. We know this is from the first solution. We now know that N3 is 1 for air. We're going to assume it's 1, and we need to know theta 2 prime and theta 3. We can apply this again, law of reflection, and of course, Snell's law for refraction, N3 sine theta 3 equals N2 sine theta 2, and again, remind ourselves with respect to the normal. The 29 degrees is an angle of reflection with respect to the normal, and they want it with respect to the surface 2, 3. So subtract it from 90 degrees, you get 61. Okay, now we still have Snell's law, and we're going to solve this for theta 3. It'll be the inverse sine of N2 over N3 times the sine of theta 2. And again, reminding ourselves. And theta 3 will be the inverse sine of 1.77 divided by 1. The 1 comes from the fact that it's air, and we're going to assume it's close to 1. Sine of 28.88 degrees. And this turns out to be 59 degrees. And that's the angle of refraction in medium 3 with respect to the normal. Now we checked this. We expected this to bend away from the normal. And it did. Theta 3 is greater than theta 2. Because the light speeds up, it can bend away from normal. Okay, now that was with parallel surface. Now we're going to do something with a little bit more complicated. Instead of parallel surfaces, we have a prism. And a parallel beam of light consisting of two wavelengths, lambda 1 of 400 nanometers, lambda 2 of 650 nanometers, enters silicate plate glass prism, equilateral prism, at an angle of 45 degrees of the normal of one face. At what angle does the beam leave the prism relative to the normal of that face? So you're asking for this angle here. Now, the light is going to split up. It's going to disperse because the index of refraction for flint glass at 400 nanometers is 1.665. It's higher, as expected, than the index of refraction for flint glass at 650 nanometers. Okay, so the first thing you want to do is draw yourself a picture. Here's your prism. Here is the angle of incidence coming in relative to the normal. Here's the light path. When it encounters this interface here, it's going to medium of higher index of refraction, so it's going to bend toward the normal. Then it will come and encounter this medium here. And you got to draw another normal here, and we're looking at this angle, and when it comes out, it's going to have a greater angle because the medium goes back to close to 1 here, okay? Comes out into air. Okay, so it can bend away from this normal. The physics of this is refraction chromatic variation, and we know that N1 equals air, and that will also equal N3, which this is N1 and N3. And with this, we have N2 at 400 nanometers is 1.665, and N2 at 650 nanometers is 1.619, and theta 1 is 45 degrees. We have N1 sine theta 1 equals N2 sine theta 2, and at theta 2 is going to be the inverse sine of N1 over N2 divided by times sine theta 1. At the first surface, N1 is 1, so we can plug that in here, and we also know the angle is 45 degrees. We can reduce that to this. Theta 2 equals the inverse sine of 0.707 divided by N2. At this point, we plug in for our wavelength 1, we plug in its index of refraction into this equation, and we wind up with 25.13 degrees. For this wavelength, we plug in its index of refraction, and we wind up with 25.90 degrees. Now we need to get this incident angle at the second surface. Okay, so this is just repeating what we had before. So we need the incident angle at the second surface. And you probably remember this from geometry or something. The sum of the angles in any triangle is 180 degrees. And of course, this is an equilateral triangle. So this is 60 degrees, that's 60 degrees, that's 60 degrees. And there's another little triangle in here that consists of the apex of this prism plus this angle here and that angle, which is set up by the path of light through the prism. So we had to remember that theta 2 is with respect to the normal of the surface, but we want theta 3 to also be with respect to the normal of the surface. So we can use that, plug that in to the fact that you have three angles here that have to equal 180 degrees. This, of course, is this angle right here. This angle is this angle here. This angle is that angle there. Now, of course, we've reduced this and we solve this for the incident angle. Theta 3 will be 60 degrees minus theta 2. We're going to need that to go to the next surface, from one surface to the next. This is repeated from the previous part, and now we know that theta 3 is 60 degrees minus theta 2. So for 400 nanometers, we have to take the one for 400 nanometers and apply it to that formula. We come up with 34.87. Similarly, for the 650 nanometers, We apply this formula again to this part, and we come up with 34.10. Now, at the second surface, the light is going from glass to air. So N3 is 1, N2 at 400 is 1.665, and N2 at 650 is 1.619. We have N2 sine theta 2 equals N3 sine theta 3. And of course, N3 is 1, so that really simplifies things. So say theta 3 is now the inverse sine of N2 sine theta 2. And for the 400 nanometers, we can plug in its N2 at 400 nanometers and its angle, be careful with this, so it ends up at 72.16 degrees for 400 nanometers. Similarly, we do the same thing for the 650 nanometer light, and we wind up at 65.20. The difference in angle here is called the dispersion. And this is the reason a prism splits white light up into colors. Each one of these different colors has a slightly different index of refraction, and it's a smooth curve as they go from a low index of refraction for red to a higher and higher as you go through the orange, yellow, green, blue, violet. So they are spread out in this beautiful rainbow color. Now, total internal reflection, I like to call TIR, T-I-R. So if you hear me talk about TIR, that's what this is. There's some trick questions in here. TIR only occurs if the incident beam is in the medium with a higher index of refraction. And again, all angles are measured relative to the normal of the interface between the two media. I cannot repeat that enough because that's where most people make their mistakes. So you have a source down here, the laser pen lights shining up. If it is parallel to the normal here, or perpendicular to the interface, nothing happens. There's no bending at all. Now, most of the light goes right through. Some of it gets reflected off the bottom of the surface back down toward the source. Kind of a boring part. But the interesting thing starts to occur when you start to change this angle here of the source. So your laser pointer is now pointing here. Now you have some of the light gets reflected back. Angle of incidence equals angle of reflection. And some of it gets refracted out. And since the top medium is faster than the bottom one, it'll start bending away from the normal. As this angle increases, this refracted ray bends further and further away from the normal, and the reflected ray also bends further and further away from the normal. Eventually, you come to the point where this will lie along the surface. Also, that occurs in this time is that refracted ray gets weaker and the reflected ray gets stronger. When you have this certain critical angle here, there's a certain critical angle where the refracted ray lies just under the surface. That's a point where the angle of refraction, remember the angle of refraction is this relative to this normal here, is equal to 90 degrees. And this, the angle of incidence then, is the critical angle for TIR. And we give that the symbol theta C for critical. At this angle, the refractive beam lies just under and along the surface. And beyond this angle, all the light is reflected. So the refractive beam disappears. Becomes like a perfect mirror. And you can see here, there's a surface here. The vertical one goes straight up. Notice as this gets further and further out, it bends further and further away from the normal. And you get far enough out, and it comes back down here. And notice here, here's the reflected ray here, that's weak. Here's a reflected ray from here, that's stronger. Eventually, all the light's reflected, and none of it gets refracted. You can sort of see how bright the spots are there. Now remember, this only occurs if the incident beam from the source is in the medium with a higher refractive index. All angles are measured relative to the normal, the interface between the two mediums. Now to find theta C, you're going to notice that the refracted ray is at 90 degrees. So then we said, as Snell's law, reflect that right here. So theta 2 is 90 degrees. So N1 sine theta C is N2 sine 90 degrees. Of course, what's N2 sine 90 degrees? It's N2. So theta C is the inverse sine of N2 over N1. The arc sine, you try to take the arc sine of anything greater than 1, you get an error on your calculator. Okay, because the arc sine is undefined for arguments greater than 1. So N2, if you have N2 greater than N1, you got a problem. You have to have N1, which is the incident medium where the light's coming from, the source is in. N1 has to be greater than N2. And this actually is useful. That's how fiber optic cable works. So be very careful with this. You might want a sticky note on this. Okay, now what does a fish see? You're a fish and you're underwater. What do you think the fish see when he looks up toward the surface? Actually, and you can do this in a pool. I used to do this all the time. Look up, get underwater and look up toward the surface. As you look up toward the surface, you see distorted vision of the surface. And then as you look past a certain angle, and we're going to find out later that's a critical angle, you start seeing the sides and bottom of the pool. You don't see the surface over here. You don't see the stuff that's above the surface. So what happens is the fish's view is above the water set by the critical angle for the total internal reflection, which is the angle which the beam of light no longer emerges into the air above the surface. And remember, this is perfectly reversible. It doesn't matter whether you got the light coming from this way or the light going that way. So you can just pretend it goes this way. Okay, so the physics of this is the knowns and it's the physics of this, and we know the knowns and unknowns. So we can look up water. N1 is 1.33. Air N2 is 1. Okay, remember you're in the higher index of refraction, or else it's not going to occur. So this has to be greater than that, and we need theta C. Okay, and we've used the 1 for critical angle tier. Theta C will be the inverse sine of N2 divided by N1. It's the inverse sine of 1 divided by 1.33. And this will work. Okay. If you reverse this, you'll get an error on your calculator. If you didn't, it ends up being 48.8 degrees. That's relative to the normal. That means the fish sees about 96 or 97 degree angle here, roughly. So when he looks beyond the critical angle, looks over here somewhere beneath the critical angle, all he sees is the sides or bottom of his tank or pond. Now, if you ever watch people catch fish with their bare hands, they approach them close to the surface of the water. They're putting their hands over here. That means the fish can't see them. They're putting their hands over here, and then they grab the fish. The good thing about prisms is they can internally reflect 100%. And these makes them very useful in optical instruments. Okay, they're better than a mirror. You don't have any silvering, which can wear off. And if you ever notice the old pirate movies, and they always got a long spyglass, and they look at it through one eye, okay, and the other eye is usually covered by an eye patch. So he's looking at it through his good eye, his seeing eye. But the eyeglass is long, the spyglass is long. It's because it turns out that you get real bad image degradation if you don't have a real long distance between the lens, these two lenses here. And that's a pain in the butt, okay, because you really want to look through both eyes, assuming you don't have an eye patch. You really want to look through both eyes. Because there's something about binocular vision. It's much easier to judge depth. Your eyes can work with each other and take over for each other. It's much easier to have two, and it's a real nuisance to have two spyglasses really long. So what they do with binoculars is they fold up the light path. They use the prisms in here to fold this long light path up. That way you still have good images, but you don't have to have the big, long, bulky tubes. The other good thing about this is it reinverts the image. When you look through a spyglass, the image is upside down. Here's another use for this. If you take very thin fibers of glass or transparent plastic, you shine light down these, the light will bounce off and totally reflect inside and stay inside the fibers. So light from one end of the fiber is totally internally reflected to the other end, results in nearly the same brightness coming out. These are very low loss. These are used in instrument displays, probably your car. If you take off the front panel display in your car, there's probably some of those in there. They use them for concentrating light in dental procedures. They view in accessible regions of internal organs and machinery and pipes, and for communications, fiber optic cables. Okay, example, what is the critical angle for the interface between water and lucite, and what, to be internally reflected, the light must start in which material? First thing you want to do, besides working at this problem at home, is to look up the index of refraction of water and lucite. You probably memorized water. Lucite, look it up, it's 1.51. So you need to be in the lucite because it has to be started in the higher index of refraction or else it doesn't work. The answer to that is you must start in the lucite. So in this case, then, is N1 will be 1.51. That's the one you start in, and N2 is 1.33. The solution is theta C is the inverse sine of N2 over N1, so it's the inverse sine of 1.33 divided by 1.51. If you accidentally reverse these things, you're going to wind up with something undefined on your calculator. So if you get this backwards, you'll get an error message. Okay, now checkpoints should also be answered at home in your notebook. Then when you come to view the lecture video, come to class, you want to review these things and check to see if you got them right. If you got a whole bunch of them right, you're probably doing pretty well with this stuff. It's a low stakes, actually a no stakes self-assessment. If you get a bunch of them wrong, reread the chapter, review the lecture notes. There are odd number questions in the back of each chapter that are answered at the back of the book. You can use those for additional practice. Okay, they're asking for which beams are due to refraction. Assume this light coming in from this side, that's the incident light. They're looking for refraction. Refraction is where there's a bending, when it goes through an interface. Here is a bending. It's going through an interface. Here is another bending. It's going through an interface. Okay? The other beams, this one and that one, 2 and 4 are reflection, 3 and 5 are refraction. Okay, parallel light rays cross interfaces from air into 2 different media, 1 and 2, shown in the figures below. But which of the media outside of the air is the light traveling faster? The light will be traveling faster in the one that's bent further away from the normal or less toward the normal. And that is medium 1. Remember, it's always relative to the normal, not the surface. So that means it has a smaller index of refraction and the faster speed. This one's kind of confusing. You have parallel rays. Okay, light rays are coming across those interfaces. They're going to come from medium 1 and a medium 2, and then a medium 3. What can you say about the relative sizes of the index of refraction of these medium? Well, what you're going to do is look to see whether they go away, whether the light bends toward or away. Handle it one at a time, ignoring the rest. It turns out none of the above. So the first thing you want to do is look 1 and 2. The light rays are bent toward the normal when crossing into 2. That means N2 is greater than N1. This is the faster medium, that's a slower medium. So the light compensates for that by bending toward the normal to take a shorter path. And they're bent away from the normal when going into 3. So N3 is less than N2. So we know that much. But how about N1 and N3? Because we have no relative thing here. Well, there actually is a way of doing this. Whenever you have something like this, okay, you can ignore the second medium. So you pretend the second medium is not there. And then you look at this angle here, right here, relative to that angle there. So that when you look at this angle here, this angle is greater than that one. So that means N1 is greater than N3. So the correct answer to this is N2 is greater than N1 and N1 is greater than N3. These all had to be parallel. Okay, and the way they drew them, they were parallel. Okay, to shoot a fish with a gun or to hit it with a spear, choose you aim directly at the image above or below. You aim below. Water looks shallower than it is. The fish is actually down here. It looks like it's here, but it'll actually be about 30% deeper than it looks, because this is a higher index of refraction than this is, so the light's going to bend toward the normal when it encounters this interface. So you got to aim lower. How about if instead you use a laser beam, a laser pointer? Where would you go to have the laser beam hit the fish? It doesn't matter which way the light's going. It doesn't matter whether it's coming from here or there. It's fully reversible. So the laser beam is going to follow the same light path that the light follows that you're looking at from the fish. You aim directly at the fish because the path is fully reversible. Light is traveling from a medium of an index of refraction 1.5 into one with an index of refraction of 1.2. What is the critical answer for tear? First thing you do is check. Is it going from the higher index of refraction into the lower one? Check. It is. Then you can have tear. Then you apply the equation and do a check again. Theta C equals the inverse sine of N2 divided by N1. You have 1.2 on top, that's the second material, and 1.5, which is the first material on bottom, and this is actually defined, recalculate to get inverse sine because this is less than 1. Turns out to be 53 degrees. Light is traveling from a medium with an index of refraction 1.5 into one with an index of refraction of 2.4. At this point, your brain starts to say, wait a minute, there's something wrong with this question. I'm going from a lower to a higher index of refraction. Tear will not occur. This is a trick question, and you can try it. And this one shows up on tests, so you might want to write this in your notes and make a little sticky on it or something. Tear would not occur because the incident index is lower than the second index. And you can see that by plugging it into your calculator. You can't take the inverse sine of something greater than 1. It's undefined. Which of these materials would have the lowest critical angle for tear in air? Assume the light is incident coming in from the material, not the air, because obviously it's not going to work for air unless you're using vacuum. The only thing around that has a lower index of refraction than air, the only common thing. Okay, you want the highest N, because notice the material that you're talking about, it's going to be on the bottom here. And you're going to take the inverse sine of this. So you want this to be as large as possible, because that would make this small, and you take the inverse sine of something small, it's going to be small. And it turns out 24.42, this is what kind of gives diamond its sparkle. Is light bent toward or away from the normal or not at all when entering a medium with a smaller index of refraction than that of the incident medium? It's going to speed up. If the index of refraction drops, the light will speed up. That means it can bend away from the normal because it can afford to take a longer path through the material and still get there fast. A material has an index of refraction that increases continuously from the top to the bottom. So it's sort of like what atmosphere is like. The top of the atmosphere, there's hardly any air. As you get down further and further, the amount of air increases, the density increases, the pressure increases, everything increases. So the index of refraction is greater at the ground than it is up at the top. Top, it's basically 1 because it's a vacuum. At the ground, it's slightly more than 1. Other materials can work like this too. Usually they're materials that are denser at the bottom than they are at the top. So which one of these things? How can you eliminate some stuff? The first thing you want to do is eliminate this one. This one only occurs if this index of refraction is the same all the way through this material, because it just bends once here. One of these is the correct one. Now, as the index of refraction increases, the light will slow down. And in order to compensate for that, it's going to bend increasingly toward the normal. So this one right here is going to be the correct answer, path B. And that's just what happened. The wavelength of light will also decrease as n increases, by the way, in case you're curious. It'll slow down and bend toward the normal, increasingly towards the normal, and the wavelength will also decrease. As light travels from a vacuum of n equals 1 to a medium such as glass of n equal greater than 1, which of the following properties remains the same? Well, we know the one thing that will remain the same is the frequency. Everything else changes. Why does index refraction occur at the interface between two transparent media? Read carefully. There is one best answer. What causes refraction? It's the fact that light slows or speeds up as it goes through different media. So the correct answer to this one is the speed of light is different in the two medium. Light will take the path of least time and bend toward the normal and slow medium and away from the normal and fast one. Thank you very much. Please do your homework, review your lecture notes, and good luck on any tests that you take.